Hello there and welcome to the Sleepy Space Channel. Tonight, we are going to explore one of the deepest and most unsettling discoveries in the history of science. The discovery that something invisible, something with no name that fully captures what it is pushing the universe apart. Not slowing it down, not holding it together, pushing it apart, accelerating its expansion, driving every galaxy away from every other galaxy at a rate that grows with every passing moment. And that something, that invisible, unnamed, unmeasured, deeply puzzling force, constitutes 68% of everything that exists. 68% of everything. We call it dark energy because we had to call it something. But the name is a placeholder, a label on a box that no one has yet opened. The box is there. We can weigh it by its effects. We know it is real because without it, the universe does not behave the way it behaves. But what is inside it? What dark energy actually is, where it comes from, whether it is a property of empty space itself or something else entirely, remains one of the great open questions in all of physics. And in 2025, results from one of the most ambitious surveys of the universe ever conducted suggested something even stranger, that dark energy may not be constant, that it may be changing, that the simplest version of the story may already be wrong. Over the next 2 hours and 15 minutes, we will walk through all of it. The discovery of accelerating expansion, the theoretical landscape of what dark energy might be, the future it is leading the universe toward, and the extraordinary new data that is reshaping our understanding of the cosmos right now. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours and 15 minutes, none of this is something you need to carry. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. The story of dark energy is, at its heart, a story about expectations, about what scientists were certain they knew, and what the universe, with patient indifference to human certainty, turned out to actually be doing. For most of the 20th century, the standard picture of the universe was one of deceleration, not acceleration. The universe had begun, so the understanding went, in an event of extraordinary violence and heat, a moment of expansion from a state of almost incomprehensible density that we call the Big Bang. And in the aftermath of that moment, the universe had been expanding ever since. The galaxies, all of them, were moving away from one another. Space itself was stretching. The light from distant galaxies arrived, shifted toward the red end of the spectrum. Red shifted, because the wavelengths of that light had been stretched by the expansion of the space they were traveling through. This was not controversial. Edwin Hubble had established it in 1929. The universe was expanding, and the question that occupied cosmologists through the middle decades of the 20th century was not whether the expansion would continue, but how fast it would slow down. Because slowing down, everyone agreed, was what the universe should be doing. The reason for this certainty was gravity. Gravity pulls. Every particle of matter in the universe pulls on every other particle of matter. The galaxies are distributed across unimaginable distances, and the gravitational attraction between them, summed across billions of light years, must be, everyone was confident, acting as a brake on the expansion. The question was only a question of degree. Was there enough matter in the universe to eventually stop the expansion entirely? To reverse it? To draw everything back together in a final compression that cosmologists called the Big Crunch? Or was there too little matter for gravity to achieve that reversal? In which case, the universe would expand forever, but always more slowly, always decelerating. A gradual slowing toward a cold and thin and increasingly dark future. These were the two scenarios that occupied the field. expansion slowing toward reversal, or expansion slowing toward forever. Nobody was arguing about acceleration, because acceleration made no sense. Nothing in the physics of a universe filled with matter and radiation gave any reason to expect that the expansion would speed up. There was no known force that pushed on the scale of the cosmos. Gravity pulled. And pulling was what it was doing. The measurements required to settle the question, whether the universe was decelerating toward reversal or toward forever, were difficult but achievable. What was needed was a way to measure the expansion rate of the universe across cosmic time. Not just the current expansion rate, but the expansion rate billions of years ago. Because if the universe was decelerating, then the expansion in the distant past must have been faster than the expansion today. The universe should have been moving apart more quickly when it was young, and slowing down as it aged, in the same way that a ball thrown upward moves fastest at the moment of release, and slows as gravity does its work. Before arriving at the tool that made this measurement possible, it is worth taking a few unhurried minutes to understand the history of cosmic distance measurement itself, because that history is one of the great detective stories in astronomy, a progressive series of discoveries, each of which extended the reach of human knowledge a little further into the dark. The challenge of measuring distances in the universe is fundamentally different from the challenge of measuring distances on Earth. On Earth, you can pace out a distance, use a measuring tape, triangulate with a known baseline, or simply walk from one place to another and count your steps. None of these options are available in astronomy. You cannot send a measuring tape to a distant galaxy. You cannot walk to it. You cannot even use radar, the technique that works beautifully for measuring distances to planets and asteroids within the solar system, because radar signals would take millions of years to reach nearby galaxies and return. The only thing that arrives from distant objects, in any practical time frame, is light. And light, by itself, does not tell you how far away something is. A bright star can appear dim because it is intrinsically faint, or because it is very far away. A dim star can appear bright because it is intrinsically luminous, or because it is nearby. The apparent brightness of an object in the sky, the brightness you can measure, is the product of its true luminosity and its distance. Without knowing one, you cannot infer the other from appearance alone. The solution, worked out over more than a century of astronomy, is the distance ladder, a sequence of overlapping methods, each calibrated against the previous one, extending human measurement from the nearby to the immeasurably distant in a series of steps. The first rung of the ladder is parallax, the tiny apparent shift in a star's position against the background of more distant stars as the Earth moves around the Sun over the course of a year. Because the Earth's orbit is known with extraordinary precision, the parallax angle gives the star's distance directly through simple geometry. Parallax works beautifully for nearby stars, out to a few thousand light-years. But beyond that, the shifts become too small to measure even with the most precise instruments. The Gaia Space Telescope, launched by the European Space Agency in 2013, has extended the parallax reach to roughly 30,000 light-years by measuring stellar positions with a precision of 20 millionths of an arc-second, an angle so tiny it would be the apparent width of a human hair seen from 30 kilometers away. The second rung uses a class of variable stars called Cepheid variables. Cepheids pulsate in brightness with a regular period, swelling and shrinking over days to weeks, and in 1908, a Harvard astronomer named Henrietta Swan Leavitt made one of the most important discoveries in the history of astronomy. Working on photographic plates of the small Magellanic Cloud, a satellite galaxy of the Milky Way, Leavitt identified 25 Cepheid variables and noticed that the stars with longer pulsation periods were systematically brighter than those with shorter periods. The period of the pulsation, she realized, was directly related to the intrinsic luminosity of the star. A Cepheid variable with a period of 30 days is intrinsically more luminous than one with a period of 10 days by a predictable and consistent amount. This relationship, the period luminosity relationship, now called Leavitt's law, transformed astronomy. If you observe a Cepheid variable and measure its period, you know its true luminosity. If you know its true luminosity and can measure its apparent brightness in the sky, you can calculate how far away it must be to appear that faint. Cepheids are bright enough to be observed in nearby galaxies, and they extended the distance ladder from thousands of light years to tens of millions of light years. Henrietta Leavitt worked at the Harvard College Observatory as a human computer, one of a group of women hired to analyze photographic plates at a lower salary than their male counterparts. She made her discovery while still classified in that role, working with patience and precision on data that had been collected by others with larger telescopes than she would ever have permission to use directly. The relationship that bears her name, and it did not bear her name for many decades. She died in 1921 before its full significance was recognized. Underpins every measurement of extragalactic distance that has been made since. The Hubble constant, the supernova cosmology that discovered dark energy, the DESI survey, whose results we will discuss later in this exploration. All of them stand on the foundation that Henrietta Swan Leavitt built from photographic glass plates in the first decade of the 20th century. It is worth pausing here, for a few quiet seconds, to acknowledge what her work represents. A woman working without full recognition on data she was not meant to interpret, finding a relationship of cosmic significance that would redefine human understanding of the scale of the universe. The history of astronomy is full of these quiet acts of extraordinary seeing, people noticing things in data that others had not thought to look for, extracting patterns from what appeared to be noise. The universe rewards attention. It has always rewarded attention. It will continue to reward attention in the work of the DESI survey and the Euclid telescope and all the instruments that have not yet been built. The tool that made this measurement possible was the Type 1, a supernova. A certain kind of stellar explosion that, through a sequence of physics worth exploring in detail, explodes with a brightness that is predictable and standardizable, a brightness that can be calculated from first principles, allowing astronomers to use these explosions as cosmic distance markers. As what are called, in the language of cosmology, standard candles. The idea of a standard candle is straightforward. If you know how intrinsically bright an object is, if you know how much light it actually produces, then you can calculate how far away it must be from how dim it appears in the sky. A light bulb of known wattage that appears faint is far away. The same light bulb appearing bright is close. The physics of how brightness falls off with distance is simple and precisely known. If the object's true brightness is calibrated, its apparent brightness in the sky gives you its distance directly. Type 1, a supernovae, are not perfectly uniform, but they are close enough to uniform that astronomers found a way to correct for their small variations. The mechanism that produces them involves a white dwarf star, the dense, dead remnant of a star like our Sun, in a binary system, orbiting another star close enough that material from the companion star falls onto the white dwarf's surface. As the white dwarf accumulates this stolen mass, it approaches a threshold, a critical mass called the Chandrasekhar limit, named for the Indian-American astrophysicist Subrahmanyan Chandrasekhar, who derived it theoretically in the 1930s, at which its internal pressure can no longer resist the weight of its own gravity. The white dwarf collapses in an instant and then rebounds in a thermonuclear explosion of extraordinary violence. A flash bright enough to briefly outshine its entire host galaxy, visible across billions of light years of space. Because the explosion is always triggered at approximately the same mass, the Chandrasekhar limit, roughly 1.4 times the mass of our Sun. The explosions are approximately the same brightness, and with the correction that astronomers developed in the 1990s, relating the duration of the brightening and fading to the peak brightness, they became precise enough to measure cosmic distances with genuine accuracy. Two teams set out in the mid-1990s to use Type 1a supernovae to measure the deceleration of the universe. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory in California, and the High-Z Supernova Search Team, led by Brian Schmidt at the Australian National University, and including a young astronomer named Adam Rees, who would do much of the analytical work that produced the team's final result. Both teams were looking for the same thing. They expected to find that distant supernovae from the early universe, billions of years in the past, were slightly brighter than a simple Hubble expansion would predict. Because in a decelerating universe, the expansion was faster in the past than now, and a supernova from the early universe was slightly closer than a naive calculation would suggest, because the universe had been expanding more slowly by the time its light traveled to us. Slightly closer meant slightly brighter. That was the signal they were looking for. Before turning to what they found, it is worth sitting for a moment with the full weight of the enterprise these two teams were engaged in. The measurements required observing Type 1a supernovae in galaxies billions of light-years away, galaxies so distant that the light arriving at the telescope during observations had been traveling since before the Earth existed. Each supernova was a fleeting event, brightening and fading over the course of weeks, never repeating, requiring rapid detection and follow-up observations across multiple telescopes on multiple continents. The computational resources needed to search photographic images for the characteristic brightening were only becoming available in the 1990s. The project would have been impossible a decade earlier. The statistical methods required to separate the cosmological signal from the complications of dust, intrinsic variation, and selection effects were developed in real time by researchers working at the frontier of what was technically achievable. The Supernova Cosmology Project and the High-Z team were not competing in the pejorative sense. Both knew that a result of this magnitude required independent confirmation, and the convergence of two separate teams on the same conclusion was ultimately what gave the community confidence that the result was real. Perlmutter, patient and systematic, built a large collaboration that searched efficiently and analyzed rigorously. Schmidt and Rees, moving faster with a smaller team, subjected their analysis to layers of cross-checking that left them confident enough to publish even knowing that the result was not what anyone expected. Rees in particular deserves attention here. He was a postdoctoral researcher at the Space Telescope Science Institute in Baltimore when he conducted the final analysis of the High-Z team's data. He has described sitting with the numbers and repeatedly looking for errors, for some systematic effect, some unaccounted for dust, some miscalibration, that would make the surprising result go away. He checked. He rechecked. He showed the numbers to colleagues. Nobody found the error, because there was no error. The universe was accelerating. Rees, at roughly 30 years old, was looking at the result that would eventually win the Nobel Prize, and his immediate response was not celebration, but a methodical, increasingly convinced search for the mistake he was certain must be there. The absence of a mistake is its own kind of finding. When careful people look hard for an error and do not find it, the result stands. What they found was the opposite. The distant supernovae were dimmer than expected, not brighter, dimmer. The early universe's supernovae were farther away than a decelerating universe predicted, not closer. The universe was not slowing down. It was speeding up. The expansion of the universe. And this was the result that stopped the cosmological community in its tracks when both teams announced it in 1998. was accelerating. Sit for a moment with what that means. The galaxies are not merely moving apart. They are moving apart faster and faster with every passing moment. The space between the Milky Way and the Andromeda Galaxy, between our local group and the Virgo cluster, between our cluster and every other cluster in the observable universe, that space is growing, and the rate at which it grows is increasing. Something is pushing. Something is winning against gravity on the largest scales. And whatever it is not slowing down. The result was received with a mixture of astonishment and deep skepticism. Scientists proposed alternative explanations. Perhaps the distant supernovae were dimmer, not because they were farther away, but because the early universe's supernovae were intrinsically different. Younger stars, different compositions, slightly different explosion energies. Perhaps there was dust in the way, absorbing light over those billions of light years, making things appear dimmer. Perhaps the calibration was wrong. Perlmutter's team and Schmidt and Rees's team had anticipated these objections and tested against them. The dimming was not consistent with dust. Dust absorbs blue light more than red, producing a characteristic color shift, and the color shift was not there. The supernovae in the early universe showed no obvious signs of intrinsic difference. The calibration had been checked and rechecked. The signal was real. In 2011, Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics for this discovery. The citation described their finding as showing that the universe's expansion is accelerating, driven by a dark energy pervading all of space. 30 years after two teams of astronomers went looking for evidence of how the universe would end, they had found something none of them had expected, none of them had hoped for, and none of them could explain. The universe was not decelerating. It was accelerating. And the thing causing the acceleration, filling all of space, driving all of cosmic history, constituting the majority of everything that exists, had no agreed-upon name, no agreed-upon nature, and no agreed-upon explanation. They called it dark energy, and the name has stuck, even as the understanding has not yet arrived. There is something quietly remarkable about this history that is worth pausing over before moving forward. The scientists who discovered dark energy were not looking for it. They were looking for the opposite. The measurement of deceleration, the confirmation of the expected slowing of expansion, that was the mission. The result that arrived instead was not only unexpected, but deeply, structurally inconvenient. It required something new, something not in the existing equations, something that the physics of matter and radiation and gravity, as understood through most of the 20th century, had given no reason to anticipate, and yet the universe, indifferent to the convenience of the people studying it, had arranged itself this way, had been arranging itself this way for 5 billion years, had been accelerating, quietly, while the scientists who would eventually detect it were still in school. The patience of the universe has no comparison. So what is dark energy? This is the question that the discovery of accelerating expansion immediately raised, and it is the question that cosmology has been living with for more than 25 years. The acceleration is real. Something is causing it. What is that something? The honest answer is that nobody knows. But there are serious proposals, serious frameworks, serious theoretical structures that attempt to describe what dark energy might be. And exploring them, walking through the physics patiently, without rushing, gives the listener a genuine sense of the depth of the problem and the ingenuity of the people who have spent their careers working on it. The simplest proposal, and in many ways the most elegant, traces its origins, not to 1998, but to 1917. To Albert Einstein, who was then working to apply his newly completed general theory of relativity to the universe as a whole. Einstein in 1917 faced a problem. His equations, when applied to a universe filled with matter, produced an unstable solution. The universe, his mathematics told him, could not be static. It was either expanding or contracting. And this troubled him because the prevailing view at the time, before Hubble, before the discovery of the recession of the galaxies, was that the universe was essentially fixed, eternal and unchanging on the largest scales, as it had seemed to human observation for all of recorded history. To solve this problem, Einstein introduced a modification to his equations. A new term. He called it the cosmological constant, denoted by the Greek letter lambda, that represented a kind of uniform energy density inherent to empty space, a pressure built into the fabric of the universe itself, a repulsive tendency of the vacuum, balanced precisely against the attractive tendency of gravity. With this term in his equations, Einstein could produce a static universe, one that neither expanded nor collapsed. The cosmological constant held things in place. When Hubble established the expansion of the universe in 1929, Einstein famously referred to the cosmological constant as his greatest blunder, a mistake introduced to force the equations to produce a result that matched his expectations rather than letting the mathematics speak. He removed the term. The expanding universe did not need it. Gravity was doing the work of governing the cosmos, and the cosmological constant, having been introduced for the wrong reason, was set aside. For decades it sat in the archive of abandoned ideas. And then, in 1998, when Perlmutter and Schmidt and Rees published their results showing accelerating expansion, cosmologists reached back to Einstein's discarded term and found that it fit. Not in the way Einstein intended it, not as a term to stabilize a static universe, but as a term that naturally produces acceleration. A cosmological constant in a universe already expanding does not hold things in place. It pushes them apart. Its effect grows as the universe grows, because the constant represents a fixed energy density of empty space. And as space expands, there is more empty space, and therefore more of this energy. The expansion produces more of the thing driving the expansion. The acceleration accelerates. The cosmological constant fits the observations. The number required, the value of lambda that matches the measured acceleration, can be extracted from the supernova data, and when the cosmological constant with that value is inserted into the equations of general relativity, the universe it describes matches our universe with impressive precision. The cosmic microwave background, the distribution of galaxies, the age of the universe, the geometry of space on the largest scales, all of them are consistent with a universe described by general relativity with a cosmological constant of the measured value. The problem is not with the fit. The problem is with the explanation. If the cosmological constant represents a real physical thing, an energy of the vacuum, an energy inherent to empty space itself, then quantum mechanics, the other great framework of 20th century physics, should be able to say something about what its value ought to be. Quantum mechanics describes the vacuum not as truly empty, but as seething with fluctuations, virtual particles appearing and disappearing on timescales too short to observe directly, but real enough to produce measurable effects, like the Casimir effect, the tiny attractive force between two uncharged metal plates placed very close together, caused by the suppression of vacuum fluctuations in the narrow gap between them. This vacuum energy, calculated from quantum field theory, is enormous, incomprehensibly enormous. The naive calculation of how much energy the quantum vacuum should contain, summing the contributions of all the virtual particle fluctuations predicted by the standard model of particle physics, gives a number that is larger than the observed value of the cosmological constant by a factor of somewhere between 10 to the power of 60 and 10 to the power of 120. Those are the numbers, 10 followed by 60 zeros, or 10 followed by 120 zeros. The discrepancy is so vast that it has been called the worst prediction in all of physics. The theory says the vacuum should contain an enormous amount of energy. The observations say the vacuum contains a very small amount of energy. The gap between the two is the largest numerical discrepancy between theory and observation in the history of science. There is, it should be said, no agreed-upon resolution to this problem. Physicists have proposed that some unknown mechanism, some cancellation, some symmetry, some physical process not yet understood, reduces the vacuum energy from its enormous theoretical value down to the tiny observed value. Supersymmetry, a theoretical framework that posits a symmetry between particles and their hypothetical supersymmetric partners, was for a time hoped to provide this cancellation. When the Large Hadron Collider at CERN began operating and searching for the signatures of supersymmetric particles, none were found. The simplest versions of supersymmetry, the ones that might have provided the most elegant cancellation, were ruled out. The problem remains. The cosmological constant fits the data. The physics of what it represents at the quantum level does not fit the theory. The universe behaves as if the vacuum has energy of a specific, small, positive value. The equations of quantum field theory say the vacuum should have energy of an enormously larger value. Something is missing. Something is not understood. And the gap between what is measured and what is predicted sits at the heart of modern physics, like a stone in the river, diverting everything around it, resisting every attempt to move it. Let this sit for a moment. The listener need not carry the mathematics. The point is only that dark energy, in the form of the cosmological constant, fits the universe as observed, but does not fit the universe as theorized at its deepest level. The fit to observation is good. The theoretical foundation beneath that fit is shaky. And this combination, precise measurement, uncertain explanation, is the condition that dark energy science has occupied since 1998. The second broad class of proposals for what dark energy might be goes by the name quintessence. The term is borrowed from ancient Greek cosmology, where it named the fifth element, the substance of the heavens, distinct from earth, water, fire, and air. In modern physics, quintessence refers to a class of theoretical models in which dark energy is not a fixed constant of nature, but a dynamical field, a field that varies in space and time, that has its own equation of motion, that evolves as the universe evolves. The difference between a cosmological constant and quintessence is subtle, but profound. A cosmological constant is a fixed number built into the equations of general relativity, a property of spacetime itself, unchanging and universal. Quintessence is a field, like the electromagnetic field or the Higgs field, that permeates all of space, but can in principle vary from place to place and change over time. A universe with a cosmological constant has dark energy that is exactly the same everywhere and at all times. A universe with quintessence has dark energy that might have been different in the early universe than it is today, might be slightly stronger in some regions of space than others, and might be predicted to change in the future in ways that could in principle be detected. Quintessence models come in many varieties, with different theoretical motivations and different predictions. What they have in common is the idea that dark energy is not simply a property of the vacuum, but a new physical field in its own right, a field that has not yet been discovered, that interacts with the rest of physics in ways not yet understood, and that happens to be producing the acceleration we observe. They are motivated in part by the theoretical dissatisfaction with the cosmological constant, the gap between the quantum prediction and the observed value, and in part by the hope that a dynamical field might eventually be amenable to detection, to measurement, to understanding, in ways that a fixed constant never could be. There is a third possible response to the cosmological constant problem, one that is philosophically controversial and deeply uncomfortable to many physicists, but which has received serious attention from some of the most distinguished minds in the field. It is the anthropic argument, and it goes something like this. If the universe contains not one set of physical laws and constants, but a vast ensemble, a multiverse of regions, each with different values of the cosmological constant and other fundamental parameters, then the value we observe is not the result of some cancellation mechanism or some deep physical principle. It is simply the value that is consistent with the existence of galaxies, stars, planets, and observers. A universe with a much larger cosmological constant would expand so rapidly that matter could never clump into galaxies. The universe would have remained a thin, uniform soup of particles, never developing the structures needed to form stars, and therefore never forming planets, and therefore never producing life capable of measuring the cosmological constant and finding it small. A universe with a much smaller cosmological constant, including one with a negative cosmological constant, would have either collapsed in a big crunch too quickly for stars to form, or would behave so differently from our universe that the conditions for complexity would never arise. In an ensemble of universes spanning an enormous range of cosmological constant values, observers would necessarily find themselves in a universe whose cosmological constant is within the narrow range compatible with their own existence. The small but positive value of the cosmological constant is not mysterious. It is inevitable, given that we are here to observe it. The anthropic argument, in this form, does not explain what the cosmological constant is at a deep physical level, or why the multiverse exists, or how it should be described. But it does provide a framework in which the numerical coincidence, the smallness of the cosmological constant relative to the quantum expectation, becomes expected rather than miraculous. The anthropic argument is viewed with deep ambivalence in the physics community. To many physicists, it represents a departure from the kind of explanation science is supposed to provide: a physical mechanism, a derivable quantity, a number that falls out of the equations for a reason that can be understood and tested. The anthropic argument does not produce a testable prediction. It does not say what the cosmological constant should be, only that it must be within a certain range. Critics argue that a framework that can explain any value in the observed range is not a framework that explains anything. Steven Weinberg, the Nobel laureate who made one of the early quantitative versions of the anthropic prediction for the cosmological constant in 1987, before the accelerated expansion was discovered, himself acknowledged the philosophical discomfort of the approach while maintaining that it might nevertheless be correct. The string theory landscape adds a further dimension to this discussion. String theory, the attempt to unify all of physics in a framework of one-dimensional vibrating strings, predicts an enormous number of possible vacuum states. Estimates range as high as 10 to the power of 500 distinct solutions, each corresponding to a universe with different physical constants, different particle masses, different values of the cosmological constant. If the string theory landscape is real, and if the multiverse exists as a physical entity, if different regions of a larger universe settle into different string theory vacua, then the anthropic argument is not merely a philosophical framework, but a physical one. The small cosmological constant of our universe is the value of one particular vacuum state in a landscape of inconceivably many, selected by the anthropic filter. This is beautiful as a framework and deeply unsatisfying as an answer. The listener need not carry the technical apparatus of string theory or the multiverse. The point is only that some of the most serious attempts to answer the question of what the cosmological constant is led, by a series of logical steps, to conclusions so large and so strange, a landscape of 10 to the power of 500 vacua, an infinite multiverse of universes, each with different physical laws, that they strain the ordinary meaning of the word explanation. The universe, in this telling, does not have a particular value of the cosmological constant because of a mechanism that could in principle be identified and understood. It has that value because, given a large enough ensemble of possibilities, someone was always going to observe a universe with a value small enough to allow observation. The discomfort this produces is legitimate. The question is whether the discomfort is a guide to truth, whether the fact that we find the anthropic explanation unsatisfying means it is wrong, or whether it is simply the discomfort of a species that evolved to explain things in terms of mechanisms and purposes, confronting a universe that may operate on principles indifferent to the explanatory preferences of its inhabitants. There are other proposals, more exotic still. Modified gravity theory suggests that the acceleration is not produced by any new form of energy, but by a modification to general relativity itself. That gravity on the largest scales of the universe behaves slightly differently from what Einstein's equations predict, and that this modification produces the observed acceleration without requiring any new substance. These theories face significant constraints. General relativity has been tested with extraordinary precision in a wide range of settings, from the orbits of binary pulsars to the ripples of gravitational waves. But they cannot be entirely ruled out, and they represent a genuine alternative to the dark energy framework. Phantom energy models posit a form of dark energy with an energy-to-pressure ratio even more extreme than the cosmological constant. A ratio that, if it holds, leads to a future in which the acceleration of the universe increases without bound, eventually tearing apart not just galaxy clusters and galaxies, but solar systems, planets, and ultimately atoms themselves in an event called the Big Rip. These models are constrained by observations but not eliminated. The landscape of theoretical proposals is broad, and the honest position of the field is that it remains open. The cosmological constant is the simplest model and the one most consistent with current observations. But it is not the only model. And the question of which model, if any, correctly describes the true nature of dark energy is the driving question of observational cosmology in the first quarter of the 21st century. What is worth holding on to, as the listener lets these ideas settle, is not any particular theoretical framework, but the shape of the problem. There is something in the universe, something constituting 68% of all the energy in the cosmos, that drives the accelerating expansion. It is smooth and uniform. It does not cluster. It does not emit light or absorb light. It interacts with matter only through gravity, by shaping the space-time through which matter moves. It is everywhere, in this room, in the space between galaxies, in the interior of stars, in the vacuum between atoms. And its nature, whether it is a property of space itself, a dynamical field, a modification of gravity, or something not yet conceived, is genuinely unknown. The universe is under no obligation to have answers that fit human frameworks. It has been what it is for 13.8 billion years. The dark energy has been accelerating the expansion for 5 billion of those years, long before the first ancestors of human beings walked the African savanna. It will continue for billions of years more. The investigation of what it is has been ongoing for a quarter century. The investigation has much further to go. There is something quietly restful about this, if the listener allows it. Not frustrating, restful. The question is real. The scientists working on it are serious, careful, and extraordinarily capable. The universe is not withholding the answer out of malice. It simply is what it is. And what it is takes time to understand. The patience of the investigation is, in its way, a mirror of the patience of the cosmos. Both are proceeding at their own pace. Neither is in any hurry. Where is dark energy taking the universe? This is the question that naturally follows from understanding what dark energy is doing, not its nature, which remains uncertain, but its effect, which is measurable and whose consequences can be traced across deep time with some confidence. The fate of the universe is one of the oldest questions in cosmology, and dark energy has transformed the answer from something that depended on uncertain measurements of matter density into something that depends, now, on the uncertain nature of dark energy itself. The old question was whether there was enough matter to halt the expansion. The new question is what dark energy will do over the next trillion years. Before tracing the future, it is useful to be precise about the present, about what the universe is made of right now, in this moment, as the listener lies in the dark. Because the discovery of dark energy is not the only discovery that has reshaped our understanding of the cosmic inventory. It is accompanied by, and deeply intertwined with, the discovery of dark matter. And together, these two dark quantities have produced a picture of the cosmos that is profoundly different from the one that prevailed before the 1990s. The universe we can see, the stars, galaxies, gas clouds, planets, and all the ordinary matter that emits or absorbs light, constitutes approximately 5% of the total energy content of the cosmos. 5%. The rest is divided between dark matter, at roughly 27%, and dark energy, at roughly 68%. Dark matter is not the subject of tonight's exploration, but it deserves a moment's acknowledgement because it is dark energy's constant companion in the equations of cosmology, and because the contrast between them illuminates something important about how the universe is structured. Dark matter, like dark energy, does not emit or absorb light. But unlike dark energy, dark matter behaves like matter in all other respects. It has mass, it gravitates, it clumps and clusters, it forms halos around galaxies and fills the scaffolding of the cosmic web. It was inferred from the rotation curves of galaxies, from the motions of galaxies within clusters, from the bending of light around galaxy clusters by gravitational lensing, and from the pattern of the cosmic microwave background. The evidence for its existence is extraordinarily robust. What it is, what particles constitute it, remains unknown, despite decades of direct detection experiments and collider searches. The universe, in the lambda CDM model, lambda cold dark matter, the name for the standard cosmological framework, where lambda denotes the cosmological constant and CDM denotes cold dark matter, consists of these three ingredients: ordinary matter at 5%, cold dark matter at 27%, and dark energy in the form of the cosmological constant at 68%. This model, constructed in the aftermath of the 1998 discovery, describes the observable universe with remarkable precision. The cosmic microwave background, the large-scale structure of galaxy clusters and filaments and voids, the abundance of light elements from Big Bang nucleosynthesis, the age of the universe, the geometry of space on the largest scales, all of them are consistent with lambda CDM. The model is not perfect. It has anomalies and tensions that motivate ongoing research. But no competing model describes the full range of observations as well. What is striking about lambda CDM, worth pausing over for a few unhurried seconds, is what it implies about the nature of the cosmos. The universe we can see, the universe that our entire scientific history has been spent observing and classifying and explaining, is a small fraction of what is there. 95% of the universe is dark, not merely unlit, not merely distant, but constitutionally different from the matter that makes up everything we have ever directly touched or seen. the atoms in the listener's body, the photons from the stars, the rock of the earth, and the hydrogen of the sun. All of that is 5%. The vast majority of what exists is something else entirely. Two something else's, in fact. One that gravitates and clusters, and one that expands and pushes. There is no reason to find this troubling tonight. The universe has been 5% ordinary matter since long before the first atom of the listener's body was assembled in a star. It will still be 5% ordinary matter long after every sun has cooled. The proportion has been constant for billions of years. The universe is simply arranged this way, and the arrangement is part of what makes it the particular cosmos that contains this planet, this night, this moment of quiet. The standard model of cosmology today, incorporating the cosmological constant, leads to a specific future, an increasingly cold, dark, and empty universe, expanding forever, with the rate of expansion growing without bound. Cosmologists call this scenario the heat death, or sometimes the big freeze. It is the most probable destiny of the universe, given what we currently observe. And it is a future so vast and so quiet that sitting with it for a few minutes, unhurried, without urgency, produces something like the cognitive experience of scale itself. Consider what the universe looks like today, 13.5 billion years after the Big Bang. It contains roughly 2 trillion galaxies, each containing billions to hundreds of billions of stars, spread across a sphere whose observable radius is about 46 billion light-years. It is full. By the standards of the very early universe, which was a uniform plasma, and by the standards of the very distant future, which will be nearly empty, today is a time of extraordinary richness. Stars are forming, galaxies are colliding and merging, planets are circling suns. Complexity exists. We exist. Now follow the thread forward, with the cosmological constant doing what it does, quietly, relentlessly, without pause. It may be useful, before following the thread of cosmic time into the far future, to have a clear sense of where we are on that thread right now. To understand the present moment in the context of the full history of the universe, so that the future can be seen in proper proportion. The universe is 13.8 billion years old. This figure comes from multiple independent measurements, from the age of the oldest stars, from the expansion rate of the universe, from the temperature and pattern of the cosmic microwave background, all of which converge on the same value with impressive precision. 13.8 billion years is an old age. It is 3 times the age of the Earth. It is roughly 500,000 times longer than recorded human history. It is a number so large that direct intuition fails, and analogies must be used. If the entire history of the universe were compressed into a single year, each month representing roughly 1.15 billion years, the Earth would not form until September, roughly 9 months in. The first microbial life on Earth would appear in late September or early October. Complex multicellular animals would not appear until well into December. Dinosaurs would arrive on December 25th and go extinct on December 30th. The entire span of recorded human civilization, from the first writing to the present, would occupy the last 13 seconds of December 31st. In this analogy, the listener is lying in bed at the last second of the last minute of the last day of a year that represents the entire history of the universe. And yet, the stelliferous era, the era of star formation, the era in which stars burn and planets orbit and life might arise, extends forward from here by a factor of roughly 1,000 times the universe's current age. The universe is not old in the context of what it will be. It is young, extremely, improbably young. The starlit era has barely begun. This is a perspective worth holding for a moment. the feeling of cosmic lateness, the sense that the universe is winding down, that things are fading and thinning and darkening, is technically accurate on human timescales, but radically misleading on cosmic ones. The universe has used less than 1% of its star-forming lifetime. The vast majority of stars that will ever exist have not yet formed. The vast majority of planets that will ever circle suns are not yet born. Whatever life might arise on those future planets, in whatever forms evolution will produce over unimaginable spans of time, has not yet begun. We are at the beginning of the story, not anywhere near its end. It is dark energy that will ultimately determine what that story looks like, whether the stelliferous era ends in a gradual dimming or an abrupt unraveling, whether the future contains the patient accumulation of entropy across trillions of years or the violent expansion that the Big Rip describes. The cosmological constant, holding steady, points toward the gradual dimming. Evolving dark energy may point elsewhere. The answer is not yet in. In approximately 4.5 billion years, the Sun will exhaust its hydrogen fuel, swell into a red giant, and eventually shed its outer layers as a planetary nebula, leaving a white dwarf at its center. This is a local event, a stellar event, not a cosmological one. But it is the first milestone on the timeline of cosmic aging that is worth acknowledging. The solar system, as it currently exists, has roughly as much time remaining as it has already existed. That is a long time. But on the scale of what follows, it is the first breath of a story whose ending lies unimaginably far ahead. In 4 to 5 billion years, the Andromeda Galaxy, the large spiral galaxy currently approaching us at about 110 kilometers per second, will merge with the Milky Way. This merger, which has been studied in detail using computer simulations and is one of the best constrained predictions in extragalactic astronomy, will not destroy either galaxy's stars directly. The distances between individual stars are so enormous that direct collisions between stars during a galactic merger are extremely rare. What the merger will do is scramble the orbits of stars, redistribute gas and dust, trigger episodes of intense star formation, and over the course of several billion years, produce a new combined galaxy, sometimes called Milkomeda in informal discussions, which will be elliptical in shape, having lost the spiral structure of its progenitors in the gravitational turmoil of the collision. The Sun and its planets, if they still exist, will find themselves in a different orbital environment after the merger, their relationship to the galactic center rearranged, their neighborhood altered. But the Sun's own fate, as a red giant transitioning to a white dwarf, will proceed regardless of the galactic context. The local story of our solar system is written in the Sun's remaining hydrogen fuel, and the merger of galaxies does not change that. Beyond the Milkomeda merger, the timeline lengthens dramatically. The dark energy, operating on the scale of the cosmos as a whole, begins to dominate the story more and more completely. In roughly 100 billion years, 10 times the current age of the universe, the expansion of space will have carried the vast majority of today's observable galaxies beyond our cosmological horizon. The horizon is the sphere beyond which light has not had time to reach us in the age of the universe. It is not a fixed boundary, but moves with the expansion of space. In the distant future, as the accelerating expansion continues, the horizon will shrink relative to the distribution of matter in the universe. Not because the universe is getting smaller, but because the rate of expansion will eventually be so high that light from increasingly nearby regions will no longer be able to reach us. Galaxies that are currently visible will recede beyond the point at which any signal from them can ever reach us. They will vanish from our observable universe, not by moving into darkness, but by the expansion of the space between us growing faster than light can cross it. In a universe 1 trillion years old, the Milky Way and its immediate neighbors, the local group, will be the only structures visible. Everything beyond the gravitational reach of our local cluster will have receded beyond the horizon, red-shifted beyond detection, effectively gone. An astronomer in that distant era, looking out from a planet orbiting a very old and very dim star in the Milky galaxy, would see a universe that appeared to contain only one galaxy, their own. The evidence for the expansion of the universe, the redshift of distant galaxies, the cosmic microwave background, all of it would be beyond observation. If those astronomers had no records of the science done in the cosmological present, they would have no way to know that there were 2 trillion other galaxies. They would be marooned, intellectually, in a universe that appeared to consist of a single island of stars surrounded by absolute darkness. The picture of the dark era deserves a few more words. The listener may find it useful to have a concrete image of what the universe will look like in, say, 100 trillion years, 100 times the current age, when the last sun-like stars have faded and the red dwarfs are beginning their long decline. In that era, the Milky galaxy, the merged remnant of the Milky Way and Andromeda, will exist as a large elliptical structure, its spiral arms long since scrambled by the merger, its active star formation largely over. The supermassive black hole at its center, a merged remnant of the 2 central black holes from the original galaxies, grown by accretion over billions of years to perhaps tens of billions of solar masses, will be quiet. The furious activity of quasars and active galactic nuclei, which illuminated the early universe, will be a memory written in the red-shifted light of objects beyond the cosmological horizon, inaccessible to any observer that exists. The black hole will turn slowly at the center of the galaxy, its gravity holding the stars of the merged system in their orbits, its Hawking radiation so faint as to be utterly undetectable against any background, a temperature so close to absolute zero that no technology we can conceive could distinguish it from nothing. The red dwarf stars, the oldest and most numerous of the surviving stellar population, will be tiny, dim, reddish points of light, each burning its hydrogen with such frugality that they will survive for another 10 to 100 trillion years. Around some of them, planets may still orbit. Whether any of those planets will carry life, whether biology is possible in a universe 100 trillion years old, with much cooler suns and a much thinner environment, is a question that no one can answer. The conditions are profoundly different from those that produced life on Earth. The cosmic environment has changed in ways that are hard to fully anticipate. But the laws of chemistry, the stability of complex molecules, the possibility of energy flows that could drive metabolism, none of those have changed. Physics permits complexity. Whether complexity arises is a question about initial conditions in history, and the history of those distant worlds is not yet written. In this era, if an astronomer on one of those distant planets points a telescope in any direction, the sky will be different in a way that no astronomer from our era would easily recognize. The cosmic microwave background, the faint afterglow of the Big Bang that fills our sky with thermal radiation at 2.7 Kelvin, will have redshifted further, cooling to a temperature so close to absolute zero that no instrument will detect it. The evidence for the Big Bang itself, encoded in that background radiation, will be effectively gone. The horizon will have moved inward, leaving only the immediate neighborhood of the local galaxy group in view. An astronomer in that era, without access to records from a much earlier time, would have no evidence for the Big Bang, no evidence for the expanding universe, no way to infer that the cosmos had a beginning. The universe will have aged into a kind of cosmic amnesia, the evidence of its youth hidden behind the expanding horizon. This is, it should be said, one of the more philosophically arresting consequences of dark energy, that its ongoing acceleration is actively erasing the evidence for the full scale of the universe. The universe we can observe today is the richest version of the universe we will ever be able to observe. From this point forward, as dark energy accelerates the expansion, the observable universe will contain less and less. Future civilizations will have access to fewer and fewer of the facts needed to reconstruct the cosmological history of their universe. They will inherit a smaller sky and have no way to know it. Sit for a moment with that image. The erasing, the gradual disappearance of evidence, not through destruction, but through distance. The universe becoming unknowable, not because anything has been lost, but because the scale of it exceeds the reach of any possible observation. The patience required to find this calming, rather than troubling, is the patience the universe itself has always exercised. It has never been troubled by what is hidden from view. The stars of the local group will continue forming for trillions of years, though the pace of star formation will slow as the available gas is consumed or exhausted. Smaller, cooler, more fuel-efficient stars, red dwarfs, the most common type of star in the galaxy today, will outlive all others by enormous margins. A red dwarf of the minimum mass for hydrogen fusion will burn for trillions of years, 10 trillion, 100 trillion, long after every sun-like star has faded to a white dwarf and every blue giant has exploded. The red dwarfs will hold the light of the cosmos long after everything else has gone dark. Eventually, they too will exhaust their fuel. The last red dwarf will cool and dim over periods longer than the current age of the universe multiplied by itself many times over. When it finally fades, the era of stellar light will have ended. Astronomers call this period, from today until the last red dwarf dies, the stelliferous era. We are inside it now, near its beginning, in the richest possible moment. The universe will never again contain as many burning stars as it does right now. After the last star fades, what remains will be the remnants of stellar death: white dwarfs, neutron stars, black holes, plus the cold, dark remnants of planets and clouds of gas that never formed stars. This is the degenerate era, named for the quantum mechanical state of the matter in white dwarfs and neutron stars. White dwarfs will continue to cool for incomprehensible spans of time, eventually becoming what cosmologists call black dwarfs. Cold, dark objects the size of a planet and the mass of a star, emitting no light, radiating no detectable heat, drifting silently through a universe grown almost entirely dark. The black holes will outlast even the white dwarfs. Stephen Hawking showed in 1974 that black holes are not perfectly black. They radiate a very faint thermal glow, now called Hawking radiation, produced by quantum effects near the event horizon. The rate of this radiation is inversely proportional to the mass of the black hole. Smaller black holes radiate faster, while larger ones radiate so slowly that the effect is for practical purposes unmeasurable. A black hole, the mass of the Sun, would take 10 to the power of 67 years to evaporate completely via Hawking radiation. The supermassive black holes at the centers of galaxies, with masses billions of times that of the Sun, would take something like 10 to the power of 100 years to evaporate, a number so large that it has its own name, a Google of years. But the Hawking radiation will proceed. Slowly, patiently, without urgency. The black holes will evaporate, one quantum at a time, over spans of time that exceed the current age of the universe by 100 orders of magnitude. And when the last black hole has evaporated, when its final faint Hawking radiation has dispersed into the expanding void, what remains will be a universe of photons, neutrinos, and electrons drifting through an emptiness that continues to expand forever. The universe will be cold, dark, and impossibly thin. The expansion will continue. The temperature will approach, but never reach absolute zero. The darkness will be as complete as physics allows. This is the fate described by the cosmological constant. This is where 68% of everything is sending us. It is, at some level, a strange thing to contemplate from a warm room at night. The future the cosmologists describe is billions of times more distant than any concern that will arise tomorrow morning, or next year, or in the next 1,000 years. The stars will not begin their final decline for 1 trillion years. The last red dwarf will not fade for trillions more. The era of stellar light, the era in which planets form and life might arise, and civilizations might build telescopes and look up at the sky, has barely begun. The universe is extraordinarily young, if the full timeline is taken as reference. The listener lying in bed, at this moment, exists near the very beginning of cosmic history, in one of the brightest and most active epochs the universe will ever experience. Let your breathing slow. Let the timeline settle, not as a weight, but as a perspective. The universe is in no hurry. Neither are you, tonight. The fate described above, the heat-death, the gentle and permanent cooling and dimming of everything, is the most likely future given current observations. But it assumes the cosmological constant is exactly constant. It assumes that dark energy is precisely what it appears to be, fixed, unchanging, a permanent property of the vacuum. If dark energy is not constant, if it evolves with time, as quintessence models suggest, the future changes. The degree to which it changes depends on the nature of that evolution. If dark energy grows stronger over time, if the ratio of its pressure to its energy density is less than -1, in the technical language of cosmologists, the expansion does not merely continue, but eventually diverges. The rate of expansion grows without bound, and when it grows enough, the space between objects begins to expand faster than the forces holding those objects together can compensate. Gravity, which holds galaxy clusters and galaxies together, begins to lose. Then the electromagnetic force, which holds planets and rocks and molecules together, begins to lose. Then even the strong nuclear force, which holds protons and neutrons together inside atomic nuclei, begins to lose. In a finite amount of time, everything is torn apart. Atoms, nuclei, protons. The universe ending not in a cold, dark dispersal, but in a violent unraveling called the Big Rip. Current observations constrain the energy-to-pressure ratio of dark energy to be close to -1, consistent with the cosmological constant, but not definitively equal to it. The Big Rip is possible. It is not the favored outcome, but it cannot be excluded. If dark energy grows weaker over time, if, unlike the cosmological constant, it diminishes as the universe ages, the expansion could eventually slow again, potentially allowing gravity to reverse it, leading to a recollapse. The Big Crunch, the mirror of the Big Bang, the universe contracting back to a state of extreme density. Some cyclic cosmological models propose that the universe oscillates between expansion and contraction indefinitely, each big crunch leading to a new Big Bang. Whether this is physically possible, and whether the physics of a collapsing universe allows a bounce rather than a final singularity, is an open question. The point is that the fate of the universe is not yet determined by observation. It is constrained. The range of possibilities has been narrowed. But the answer depends on the nature of dark energy, and the nature of dark energy is what we do not yet know. The trillion-year future of the cosmos is written in a substance we cannot identify, in a language we cannot yet read, and this brings us to where the science stands right now. To the results announced in 2025 from a project called DESI, the Dark Energy Spectroscopic Instrument, that have introduced into the already complicated picture of dark energy a new layer of uncertainty and, For scientists who have spent careers working in this field, a new note of extraordinary excitement. Before exploring what the DESI results actually say, it is worth understanding why a new instrument was needed at all. The supernova measurements of Perlmutter and Schmidt and Rees established that the universe is accelerating. They pinned down the approximate value of the dark energy density with surprising precision for a first measurement. But they left key questions open. The most important of these questions concerns the equation of state, the ratio of the dark energy pressure to the dark energy density, the parameter that cosmologists call W. For the cosmological constant, this parameter is exactly -1. This is a precise prediction that emerges directly from the mathematics of general relativity. A cosmological constant necessarily has a pressure equal in magnitude and opposite in sign to its energy density, producing W equals -1 exactly, always, everywhere, for all time. If dark energy is the cosmological constant, then W is -1 now, was -1 a billion years ago, and will be -1 a trillion years from now. It is a constant in the deepest sense. For quintessence models, W is not -1. It is some value between -1 and 0, or possibly less than -1, and it changes with time. The specific value and the specific way it changes depends on the particular quintessence model, on the shape of the potential energy function that governs the field. Different quintessence models predict different trajectories for W as a function of cosmic time, and in principle, a sufficiently precise measurement of how W has varied across cosmic history could distinguish between the cosmological constant and quintessence, and even between different quintessence models. This is exactly what DESI was designed to do, not to detect dark energy, that had been done in 1998, but to characterize it, to measure WU with enough precision and across enough of cosmic history to determine whether it has been constant or varying, to read the behavior of dark energy across 5 billion years of cosmic time and see whether it matches the flat line of the cosmological constant or shows the curvature of evolution. The technique of baryon acoustic oscillations, the cosmic ruler that DESI exploits, is worth understanding in some detail because it is elegant and because understanding it gives the listener a concrete picture of what DESI is actually measuring. In the first few 100,000 years after the Big Bang, the universe was a hot, dense plasma, a soup of photons, electrons, protons, and the nuclei of light elements, all tightly coupled together. The photons carried radiation pressure, which resisted the tendency of gravity to pull the plasma together. Sound waves, oscillations in the density of this plasma, propagated through it at roughly half the speed of light. These were not sound waves in the ordinary sense. There was no air to vibrate, but pressure waves, analogous to sound in structure, if not in medium. When the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, a moment called recombination, about 380,000 years after the Big Bang, the photons decoupled from the matter. They streamed freely through the now transparent universe as the cosmic microwave background, while the matter was left behind, carrying the imprint of all the sound wave oscillations that had occurred during those 380,000 years. The sound waves had propagated outward from initial density fluctuations, carrying matter with them, and when the waves froze at recombination, they left a characteristic signature in the matter distribution, a preferred scale, corresponding to the distance the sound waves had traveled in 380,000 years. This distance, called the sound horizon, is about 490 million light-years in today's universe. This preferred scale shows up in the distribution of galaxies as a slight statistical excess in the probability of finding two galaxies separated by approximately that distance. If you look at a large sample of galaxies and measure all the pairwise separations, you find that separations near 490 million light-years are slightly more common than you would expect from a random distribution. This is the baryon acoustic oscillation signal, a faint but real bump in the correlation function of galaxy positions, a fossil imprint of sound waves from the universe's first 380,000 years. The beauty of this signature is that its physical scale is known from first principles, from the temperature of the cosmic microwave background, the density of matter, the speed of sound in the early universe plasma. It is a standard ruler, calibrated by physics rather than by any particular type of object. And by measuring how the apparent angular scale of this ruler changes with redshift, how its apparent size in the sky varies as a function of how far away the galaxy population is, cosmologists can trace the expansion history of the universe across billions of years, and from that expansion history, infer how dark energy has behaved over cosmic time. This is what DESI is doing, with 5,000 robotic fibers and millions of galaxy spectra on a mountaintop in Arizona. DESI is a survey instrument mounted on the 4-meter Mayall telescope at the Kitt Peak National Observatory in Arizona, in the Sonoran Desert at an altitude of 2,100 meters. It is one of the most ambitious cosmological surveys ever undertaken. Its purpose is to measure the three-dimensional distribution of galaxies across an enormous fraction of the observable universe, not merely the positions of those galaxies, but their redshifts, and from those redshifts, their distances and velocities. DESI can measure the spectra, the characteristic light signatures, of 5,000 objects simultaneously, using a field of 5,000 robotic fiber positioners that can reposition themselves in under 2 minutes, allowing the telescope to survey thousands of new galaxies with every pointing. The goal is to map the large-scale structure of the universe with unprecedented precision, tracing what cosmologists call baryon acoustic oscillations, a pattern imprinted in the distribution of galaxies by sound waves that propagated through the early universe before it cooled enough for atoms to form. These oscillations left a characteristic scale imprinted on the cosmic structure, a preferred separation between galaxies, a statistical bump in the correlation function that acts as a standard ruler across cosmic time. By measuring how this preferred scale appears to change with distance, and therefore with cosmic time, cosmologists can trace how the expansion of the universe has varied from epoch to epoch. They can, in effect, measure the expansion history of the universe with greater precision than the supernova method allows, because the baryon acoustic oscillation scale is calibrated by the physics of the early universe and does not depend on the properties of any particular type of object. The first major data release from DESI, covering roughly 6 million galaxies and quasars observed over the first year of the survey, was published in April 2024. The analysis was extended with additional data in 2025, and the results, when they came, were striking enough to generate significant discussion throughout the cosmological community and beyond. The results were consistent with the cosmological constant in some respects, but showed hints, statistically significant hints, though not yet definitive, that dark energy may not be constant. The DESI data, when analyzed with the full range of cosmological observations, including the cosmic microwave background, the supernova data, and the baryon acoustic oscillations, preferred a model in which the dark energy parameter, the ratio of dark energy pressure to dark energy density, what cosmologists call the equation of state parameter W, deviated from the value of -1 that the cosmological constant predicts. The data preferred a value that changed over time, starting at a value different from -1 in the early universe and evolving toward -1 in the more recent past, or in some analyses, the reverse. The technical significance of this deviation was, in the initial analyses, at roughly the 3 sigma level, what statisticians would describe as a roughly 1 in 1,000 probability of occurring by chance if the cosmological constant were the true model. This sounds compelling, but in particle physics and cosmology, 3 sigma is traditionally considered suggestive rather than conclusive. 5 sigma, a 1 in a million probability, is the conventional threshold for a discovery. The DESI hints were not at 5 sigma. They were interesting, important, and sufficient to motivate significant follow-up work, but they were not, in the careful language of the field, a detection of dark energy evolution. It is important that the listener understand both what the DESI results mean and what they do not mean. They do not mean that the cosmological constant is wrong. They mean that the data is more consistent with a slightly more complicated model than the cosmological constant, with a statistical preference that is real and worth taking seriously, but not yet definitive. They mean that the question of whether dark energy is constant or evolving is now more open than it was 5 years ago. They mean that the simplest model, the placeholder answer, may need to be replaced by something richer, or they may turn out to be a statistical fluctuation that disappears with more data. What makes the DESI results significant beyond their immediate statistical weight is the context in which they arrive. This is not the first hint of tension in cosmological data. For several years before the DESI results, cosmologists had been grappling with what is called the Hubble tension, a discrepancy between 2 different methods of measuring the current expansion rate of the universe called the Hubble constant. One method, based on the physics of the early universe, as measured in the cosmic microwave background by the Planck satellite, gives a Hubble constant of about 67 kilometers per second per megaparsec. The other method, based on measurements of the distance ladder, Cepheid variable stars, and Type 1a supernovae in the local universe, gives a Hubble constant of about 73 kilometers per second per megaparsec. These 2 numbers disagree by about 8%, and the disagreement has persisted and strengthened as the measurements have become more precise. This is unusual. In science, when a measurement becomes more precise, discrepancies between different methods typically resolve. Either the measurements converge, revealing that the earlier discrepancy was due to systematic errors, or one of the methods turns out to have a flaw. The Hubble tension has done neither. As each method has improved, the 2 values have remained stubbornly apart. The statistical significance of the tension is now above 5 sigma, meaning that if the universe is exactly described by the standard cosmological model, the probability of seeing this discrepancy in the data is less than 1 in a million. The Hubble tension and the DESI hints about dark energy evolution may be related. Some modified cosmological models in which dark energy evolves over time, or in which the early universe contained additional ingredients not in the standard model, can simultaneously accommodate both the Hubble tension and the DESI hints. They are potentially 2 pieces of evidence pointing in the same direction, toward a universe that is more complicated than the simplest version of the standard model. Whether they are in fact connected, and if so, how, is one of the active questions in cosmology right now. The scientists working on this, among them Mustafa Ishak at the University of Texas at Dallas, who has led significant work on dark energy constraints. Dragan Huderer at the University of Michigan, who has spent a career developing the statistical methods used to constrain dark energy, and the large international collaboration behind DESI itself, which involves hundreds of researchers at dozens of institutions across multiple countries, are not in a state of crisis. They are in a state of engaged uncertainty, which is the condition science is most at home in. The data is pointing somewhere interesting. The pointing is not yet precise enough to read the destination clearly. More data is coming. DESI is not finished. The survey planned to collect spectra for 40 million galaxies and quasars over 5 years of operation. The initial results represented 1 year's data. As additional years of data are incorporated into the analysis, as the statistical precision of the measurements improves, and the range of cosmic history covered expands, the hints will either strengthen into detections or fade into noise. The answer to whether dark energy is constant or evolving may come from DESI itself within the next several years. Other instruments are adding to the picture. The Euclid Space Telescope, launched by the European Space Agency in 2023, is conducting its own wide-field survey of galaxies, designed specifically to probe dark energy and dark matter. The Rubin Observatory Legacy Survey of Space and Time in Chile, beginning its decade-long survey of the southern sky, will photograph billions of galaxies and measure hundreds of thousands of Type 1a supernovae, adding precision to the supernova cosmological measurements that made the initial discovery. The Nancy Grace Roman Space Telescope, NASA's next large space observatory, will combine wide-field imaging with spectroscopic capability to probe dark energy from multiple angles simultaneously. The next decade will be, by the assessment of many working cosmologists, a decisive period for dark energy science. The instruments are built, or nearly built. The methods are established. The data is accumulating. The question is whether the universe will cooperate, whether the signal of dark energy's nature, if dark energy has a nature more complex than a cosmological constant, will emerge clearly enough in the data to be identified unambiguously. It may. Or the cosmological constant may be confirmed as the correct description, and the hints in the DESI data may resolve as statistical noise. Both outcomes would be profound. The confirmation of a pure cosmological constant would deepen the mystery of the vacuum energy, the enormous discrepancy between the quantum prediction and the measured value, and force a serious reckoning with what mechanism could produce such an exact value. The detection of dark energy evolution would open an entirely new chapter of physics, the study of a new field, its properties, its interactions, its implications for the future of the universe. The listener need not carry any particular preference for which outcome is correct. The universe will be what it is, regardless of what would be more elegant or more convenient for the physics. What the listener can carry, if it is useful, is the sense of a field in genuine motion. Scientists with real instruments making real measurements, the data pointing somewhere interesting. The answer not yet in hand, but closer than it has ever been. The investigation is alive. The question is open. The universe is not yet done with its surprises. Something in that openness is worth a moment of unhurried attention. The greatest questions in science are not problems awaiting solutions. They are conversations between human curiosity and cosmic indifference, conducted across incomprehensible distances and timescales, using instruments of extraordinary ingenuity, in the service of understanding something vast enough to hold all of human history in a single corner of a single galaxy. The DESI results are one sentence in that conversation, important, suggestive, partial, and preliminary. More sentences are coming. And yet, even as the instruments accumulate data and the statistical precision of dark energy measurements improves, there is a boundary to the investigation that no instrument can cross. A limit, not of technology, but of physics. A horizon built into the structure of the universe itself, beyond which knowledge, in the deepest sense, becomes impossible. The cosmological horizon is the sphere surrounding us beyond which light has not had time to reach us in the age of the universe. Beyond the horizon, roughly 46 billion light-years away in every direction, there may be more universe, extending for unfathomable distances or perhaps forever. There may be other galaxies, other stars, other planets, other configurations of matter that have never affected us and that we have no way of observing. If the universe is infinite, the cosmological horizon encloses a finite portion of an infinite whole, and the portion we can observe is not representative of the whole in any way we can verify. This is not merely a practical limitation. It is a principled one. The finite age of the universe, combined with the finite speed of light, means that there is a maximum distance from which any signal can have reached us. Information travels at the speed of light. The universe is 13.8 billion years old. No information originating more than 13.8 billion light-years away. Adjusted for the expansion of space, which extends the figure to 46 billion light-years, can have reached us. What lies beyond is, in the most literal sense, beyond our knowledge. Not merely unknown, but unknowable. Not merely unmeasured, but unmeasurable. Not merely unseen, but unseeable. For as long as physics, as we understand it, holds. The dark energy that fills the observable universe may fill the space beyond the horizon in exactly the same way. Or it may be different. Or there may be regions beyond the horizon with no dark energy at all. Or the very laws of physics may differ beyond the horizon. Different values of the fundamental constants, different numbers of dimensions, different histories. There is no way to know. And the accelerating expansion caused by dark energy ensures that this boundary is not merely static, but actively shrinking. That regions currently just inside the observable universe are being carried beyond the horizon as the expansion accelerates. The universe we can observe is getting smaller, not in absolute terms, but in terms of what fraction of whatever total universe exists it represents. This is among the deepest implications of dark energy, the one that is least often discussed, but most philosophically significant. The force we discovered in 1998 is not merely driving the fate of the galaxies, it is limiting the scope of what can ever be known. Every moment that the expansion accelerates, some infinitesimal amount of the potentially knowable universe crosses beyond the horizon and is lost. Not destroyed. Those distant regions continue to exist in whatever state they are in, regardless of whether we can observe them. But they leave the domain of our science. They become part of the universe we cannot speak to, the cosmic territory that will never write back. The degenerate era and the black hole era deserve brief portraits as well, because they are the chapters of cosmic history that will occupy the greatest span of time by an almost incomprehensible margin. After the last red dwarf fades, somewhere between 10 trillion and 100 trillion years from now, the universe enters a period where no new energy sources are being generated by fusion. The remnants of stellar evolution, white dwarfs cooling toward black dwarfs, neutron stars spinning down through the loss of rotational energy, black holes accreting what little matter remains available, will be the dominant objects. The temperature of the universe will continue to fall. The density will continue to decline. The expansion will continue. A white dwarf cooling toward a black dwarf does so on a timescale that is staggering even by cosmic standards. The current universe is not yet old enough for any black dwarfs to exist. The cooling time is estimated at roughly a quadrillion years, 1,000,000 billion years, a number so large that no unit of human time usefully conveys it. But the white dwarfs are cooling. They are cooling right now, as the listener lies in bed, imperceptibly and continuously. The white dwarf remnant of our sun, if the sun's life cycle proceeds as predicted, will cool for quadrillions of years after the Earth has long since been engulfed by the red giant that the sun will become. It will cool to the temperature of the cosmic background, and then to the temperature of whatever the cosmic background is at that time, and then perhaps cooler. At some point, deep in the black dwarf era, even the protons in the matter composing these cold dead stars may decay. The proton lifetime is uncertain, but many theoretical frameworks predict it to be finite. And the black dwarfs themselves will slowly dissolve, their matter converting to lighter particles and then to radiation, on timescales of 10 to the power of 32 or more years. The black holes will be the last objects of cosmological significance, quietly evaporating through Hawking radiation, each at a rate inversely proportional to the square of its mass. The stellar mass black holes will be gone in roughly 10 to the power of 67 years. The supermassive black holes will linger until roughly 10 to the power of 100 years, a number called a googol, and the origin of the name of the search engine. After the last black hole has evaporated, there will be no objects remaining in the conventional sense. There will be a thin gas of photons and leptons, electrons, positrons, and neutrinos, dispersed through an expanding universe so vast that the average density will be essentially zero. The expansion will still be occurring. The dark energy, or whatever succeeded it, will still be pushing, and the universe will continue in this state, cold, thin, dark, expanding, essentially forever. Not quite forever. Quantum mechanics allows for the possibility of rare fluctuations, events of extraordinary improbability that might, in a universe that exists for an infinite time, occasionally produce brief episodes of structure. But these fluctuations are separated by timescales so enormous that they have no practical significance for any conceivable form of experience. This is the heat death. This is where we are going, most probably, unless dark energy turns out to be something other than a constant. It is a future that defies any ordinary intuition about endings, because it does not end. It simply becomes more and more nothing, a nothing that is still technically a something, because space still exists and is still expanding. The universe's final state is not an absence. It is a presence so thin, so cold, and so dispersed that the word presence stretches to its breaking point. There is genuine debate in the physics community about how to interpret this. Some physicists find it deeply troubling. The idea that a large fraction of existence, perhaps the majority of it, is permanently inaccessible to science is uncomfortable for a discipline devoted to understanding reality. Others find it unremarkable. Science has always proceeded from within the horizon, has never had direct access to what lies beyond it, and has managed to learn an extraordinary amount about the universe from the finite sample it can observe. The progress from Galileo to Einstein to Hubble to Perlmutter was made entirely within the observable universe, using light and matter and instruments constructed from local materials. The cosmological horizon is a limit, but limits have never stopped science from proceeding within the region where it can reach. There is also the deeper question of what dark energy, whatever it turns out to be, ultimately implies about the structure of reality. If dark energy is the cosmological constant, if it is a fixed property of space-time itself, then it suggests that the vacuum has a structure, that empty space is not nothing but something, that the geometry of the universe has a preferred energy state that it occupies, and that happens to be accelerating the cosmos apart. If dark energy is a field, then the universe contains a new ingredient, not in any current theory, a field whose properties remain to be discovered, whose interactions with matter and radiation await measurement, whose origin and fate are open questions. If dark energy reflects modified gravity, if Einstein's general relativity, the most precisely tested theory in physics, requires adjustment on the largest scales, then the framework within which all of modern cosmology is conducted needs revision. All three of these possibilities are consequential. All three require extensions to current knowledge. None of them is the kind of comfortable confirmation that leaves a field unchanged. The discovery of dark energy was not the solution to a problem, but the opening of one, a wound in the map of physics that has been kept open for 25 years, through which new ideas continue to flow without yet converging on an answer. What is perhaps most remarkable is how familiar this situation is in the history of science. Newton's gravity explained the orbits of the planets and the tides of the oceans and the trajectories of cannonballs, but it could not explain what gravity was. The answer to that question required Einstein, 200 years later. Einstein's general relativity explained the precession of Mercury's orbit and the bending of light around the sun, and it introduced the cosmological constant, which he discarded, and which turned out to be real after all. Physics advances by solving problems and discovering deeper problems behind them. Dark energy is the deep problem behind the expansion of the universe. Whatever lies behind dark energy has not yet been found. The investigation will continue. The instruments are running. The data is accumulating. The theorists are proposing. The observers are measuring. The conversation between human curiosity and cosmic reality is ongoing, conducted from a small planet in the outer reaches of a spiral galaxy, with instruments of extraordinary sensitivity, aimed at objects billions of light years away, asking questions that may not be fully answered in any human lifetime. The universe is patient. It has been accelerating for 5 billion years without needing to explain itself. The dark energy has been present through every moment of human history, through every civilization, every night sky, every astronomer who ever looked up and wondered. It was there when the cave paintings were made, and when the pyramids were built, and when Henrietta Leavitt measured the light curves of stars on glass plates in a dim room in Cambridge. It will be there long after the last star has cooled and the last black hole has evaporated. It is the most pervasive thing in the cosmos, and it is the thing we understand least. There is something quietly right about that. The universe reserves its deepest mystery for what fills it most completely. The full picture of dark energy is waiting. It has been waiting since the moment the universe began. It can wait a little longer. And so, tonight, having walked through the discovery that the universe is accelerating, through what dark energy might be, and what it is almost certainly not, through the unimaginable future toward which it is guiding everything, through the hints of a changing cosmos in the most recent data, and through the principled limits that a finite horizon places on what can ever be known, we let the question rest where it has always been. Open, genuine, in good hands. The scientists at their computers, at their telescopes, in their seminar rooms, and their late-night collaborative sessions. They are carrying the question forward with care and rigor and genuine passion. You do not need to carry it tonight. You can let it rest with them. The cosmological constant, whatever it ultimately is doing what it does right now. In the space between the walls of this room, in the space between the galaxies, in the space between the atoms of the air you are breathing. It is the most ubiquitous thing in existence, and it is perfectly quiet. It exerts no force you can feel. It makes no sound. It asks nothing of you. It simply is, as it has always been, filling the fabric of everything with the gentlest and most persistent pressure, outward, outward, always outward. The Milky Way turns on its axis as it has turned for 10 billion years. The sun moves through its orbit around the galactic center as it has moved for 4 billion years. The Earth turns beneath the night sky as it has turned for 4.5 billion years. All of it, turning and moving and expanding, slowly, patiently, at the pace of deep time, which is the only pace the universe has ever known. Let your breathing slow. Let dark energy settle around you, present and invisible, and asking nothing. Let the expanding universe continue its expansion as it has continued for every moment of your life and every moment before it. None of this asks anything of you tonight. The galaxies will still be there in the morning. The cosmological constant will still be doing what it does. The DESI telescope will still be collecting light on Kitt Peak. The question will still be open. And somewhere, in the quiet of a universe, 2 hours wider than it was when we began, a photon released at the edge of the observable universe is crossing the last of its distance, carrying no message, knowing no destination. The simplest